Hi, my name is Jose Parra, and this is our proposed model architecture. This model is built upon the forward network operator framework, which enables efficient learning of fluid dynamics problems through spatial temporal mappings. The problem architecture begins by processing an input tensor, which is where B is the batch size, T is the temporal dimension, C is the channel containing the number of field quantities, H is the spatial height dimension, W is the spatial width dimension. The input channel C contains 5 quantities of input, which are the x direction velocity U, the y direction velocity V, density, pressure, and temperature, with each quantity stored in a 2D array index with respect to the field's spatial dimensions, and the temporal dimension T is projected onto these fields with a third dimension respecting the field data with that respective temporal quantity. So onto our convolution layer. We did a convolution layer for our time, um, where our t's respective field variable quantity. We do a temporal time step, so we have 9 for each of these 5 inputs. Explain our architecture. Let's say for the density, we grab each of our time step datas, and we convoluted the layers together in order to put them in our forward network operator. As you can see, this temporal convolution layer, it grabs the first couple inputs and it does a forecast horizon and kind of just moves along the line for each of our layers. So this is our forward network blocks. This kind of explains how we did our forward network operator. As you can see, the forward network operator processes the framework spatial featuring FNO blocks. First, we have this doing 4 separate blocks. First, we have this spectral layer. It applies the 2D forward transform to map the spatial data into a frequency domain. It also learns spectral weights controlled by hyperparameter modes to suppress high frequency noise and emphasize dominant patterns, just so we won't bounce around and get too much noise on our data and make it look like blurry. It also uses inverse forward transform to return the data to the spatial domain. So after we do all that math and we want our original data back or something similar, then we add a convolution layer, which perform pointwise convolution across the spatial domains to capture more localized parameters and low frequency effects, not addressed by the spatial layer. Next, we do an activation function. We use a Gaussian error unit, which is a GELU, to enhance the model's ability to learn complex spatial temporal relationships. Next, we do a fully connected layer, which combines everything. It combines process features. It also passes them to the next FNO block or output layer in the final block. So this is our trainer. We use a LMW optimizer. The training data was generated via our benchmark problem with density, velocity, pressure, and temperature fields stored with respect to the space and time. These fields were mainly stored in the 386 by 258 arrays, which was like resolution, um, which we got field data from our CFD from our Navier-Stokes equation. But this is where each of the index of the array represents a Cartesian coordinates equivalent form from the corresponding index array position. 9 time scales were stored in order to correspond to simulation 1 through 9 with 1 second increments. Given the scale of the data fit was fit into a single batch for training. We also kind of didn't use too big of time increments or too many like time steps, just because it was already too much data for the training to handle. So this is our model after training. As you see, this is the on the fifth quant. This is our approximate data after model fitting for the 9th second. First starts off, as you see in the first square of the first column for each of these. Um, it starts off at 5, it goes to 6, 7, 8, which are all true models, and 9 is a predicted. As you see, there's slight noise, which kind of shows like it's not like a perfect fit. It doesn't have the perfect ability to capture everything with a sharp and fine gradients. Maybe we needed to make a finer mesh for our simulation. It could also be due to the FNO that capture global interactions and long-range dependencies through which may undermine localized and lower frequency models in the model. Another reason may be for the blurriness. Could be due overfitting, to be honest. So our overall mod performance was really good for the Fourier neural operator. It has successfully captured large-scale dynamics of the fluid flow properties with the mixing chamber for these gate parameters, which are pressure, temperature, density, and velocity components. This is kind of explaining the previous slide. As you saw, like the first four squares with the presented the true state of flow properties. Last square was the model's predicted state, which closely resembles a true state. There's slight blurriness in the prediction, which could be attributed to sharp grade, to like not too sharp of gradients. It doesn't potentially like grab like perfect turbulent models, or or it could be like overfitting, as mentioned in the previous slide. So in conclusion, in this study, we have been able to show the potential of the forward neural operator framework for the surrogate model in real-time fluid dynamics application with efficiency and scalability of the FNO. Complex transient fluid behaviors can significantly improve with less computational overhead. The benchmark problem involving two-phase flow in the mixing chamber has successfully tested the capability of the framework to approximate the Navier-Stokes solution, operated both accurately and efficiently. Our results suggest that the integration of data-driven surrogates model made with physical-based methodologies provides a promising avenue to solve challenges related to the computational efforts within fluid dynamics.